Okay, welcome to the chapter on amines and amines. You notice one of my favorite amines here, caffeine. One thing you should notice about amines is that similar to alcohols, amines are, well, as alcohols are derivatives of water. If you remember, we replace one of the hydrogens of water with an alkyl group. So instead of HOH, we now have an alkyl group attached to an OH. With amines, what we've done is replaced one or more of the hydrogens. Right? So in ammonia, there's 3 hydrogens. What we do is we replace at least one of them with an alkyl group. Now, it doesn't have to be a methyl group. It can be any size alkyl group, but to keep things simple, replace it with a methyl group, and we have 2 hydrogens. This is what we have here is one carbon-nitrogen bond, and we refer to this as a primary amine. Okay, so primary amines, we've replaced one of the 3 hydrogens with a methyl group. Secondary amines, we replaced 2 of them, so now we have 2 alkyl groups attached. And notice this is different from how we classified alcohols. If you remember, for alcohols, we were not looking at the nitrogen. We were looking at, with alcohols, we were not looking at the oxygen of the alcohol. So let me see if I can draw an alcohol here with this goofy pen. Alright, so with an alcohol, we have a carbon bonded to an OH. We replaced one of the hydrogens of water with an OH. This carbon is what we were looking at. So it would be analogous to looking at one of these carbons. Right? So here, this, if there's one alkyl group attached, it's primary. If there's 2 alkyl groups attached, it's secondary. If there are 3 alkyl groups attached, it's a tertiary alcohol. So we're looking at the carbon. With amines, we don't look at the carbon, we look at the nitrogen, and we ask how many carbon-nitrogen bonds are there. So to name amines, and we'll just be naming simple amines, this is similar to how we named alcohols, at least the common names for alcohols. We name the alkyl group, and then we say amine. So if this was an alcohol, so if it was a 2-carbon alcohol, if you recall, right? So let's make this carbon, OH. Okay, so we would say this is ethyl alcohol. Well, all we do now is we say, okay, it's ethylamine. What if there's 2 methyl groups attached? Well, then we say dimethylamine. By the way, these 2 are isomers. They have the same chemical formula, but one is primary. It's only 1 carbon-nitrogen bond. Here we have a secondary amine, 2 methyl groups, so dimethyl. Or we could have all 3 replaced. This is a tertiary amine, and we have different groups. And so when we have different groups, we're going to alphabetize them. E comes before M. So we're alphabetizing on the M, not on the E, or not on the D, rather. So ethyl comes before methyl. So it's ethyl dimethylamine. All right. How would we name this guy? Well, we have, there's an amine here, right? So there's 1, 2, 3 carbons. If you remember our little mnemonic, Mary eats pears. So P is for propyl. This is propylamine. This one here is that ethyl dimethylamine we saw on the previous page. Okay, so as I was saying, we have propylamine. Now they call this 1-propylamine, but all that refers to is that it's on the first carbon here. Remember, we had also isopropyl. If it was on this 2nd carbon, we'd have an isopropyl group attached. So that's what this 1-propyl means. Maybe I can see if I can draw a isopropylamine. So again, this is a primary amine, so there's two hydrogens in a primary amine. And we have one carbon-nitrogen bond, right? So there's one carbon-nitrogen bond, but then this carbon has two other carbons attached to it, like this. And then this would be still a primary amine, right? One nitrogen carbon bond. This is a secondary carbon because there's two carbon-carbon bonds attached to it. But remember, for alcohols, we're looking at the carbon. For amines, we're looking at the nitrogen. Aromatic amines, I mentioned aniline. I don't really care too much if you remember how to name something like this. This would be 3-chloroaniline. Because we're calling it aniline, this carbon here that the nitrogen is attached to automatically becomes carbon number 1. So we number them 1, 2, and 3 here. Or you could say metachloroaniline. The N-methylaniline, the N here stands for the nitrogen. So the methyl is attached to the nitrogen. So N-methyl, it's highlighted in orange or red here. The N tells you where the methyl is, because we could also have a methyl group attached to the ring. That would be a methylaniline as well. So instead of saying chloro, say it was a methyl group here, it would be 3-methylaniline. Well, to avoid that confusion, we put an N here. The N stands for this N, this nitrogen. So we talked a bit about the classification and naming of amines. Now we should talk about the physical properties of amines, the boiling point and melting point and so forth. So if you look at plain old ammonia, has a very low boiling point, -33 degrees. It's a bit unfair to compare methylamine simply to ammonia because methylamine is bigger. But what I'd like you to do is let's look at something like let's look at these two here. We have dimethylamine, so there's a methyl here, so dimethylamine is a secondary amine, and then we have this primary amine, ethylamine. Again, these two guys are isomers. We have two carbons. So when you're looking at any compounds with regard to boiling points and melting points, we want to compare compounds that are similar size. So you can do that here with methylamine and methyl alcohol. What you notice with alcohols is they will have a higher boiling point than a similarly sized amine, so 65 versus -7. Still, this is a gas at room temperature, whereas methanol is clearly a liquid. Here you see the same sort of thing. Now, ethanol, a boiling point of 79. This is grain alcohol, or alcohol in beer, wine, and distilled spirits. 79 degrees Celsius. They're about the same size, all three of these, but you notice the amines have much lower boiling points. And the reason for that is nitrogen isn't nearly as electronegative as oxygen is. So if we look at an oxygen hydrogen bond, and we can look at a nitrogen hydrogen bond, and you don't have to memorize these numbers, but the electronegativity of oxygen is 3.5. That of hydrogen is 2.1. Nitrogen is fairly electronegative, but not nearly as electronegative as oxygen. So it's 3.0, and again, hydrogen still 2.1. So what that means then, of course, is the oxygen-hydrogen bond is more polar than the nitrogen-hydrogen bond. And if you think of these molecules, these polar bonds, as little bar magnets, we have a much stronger magnet in an oxygen-hydrogen bond than in a nitrogen-hydrogen bond. And it's the hydrogen bonds that gets disrupted when you boil these things and they go into the gas phase. And so if the oxygen-hydrogen bond here sets up stronger hydrogen bonds between molecules of methanol, it's going to have a higher boiling point. See that again here with the secondary, or with the 2-carbon amines. But what's going on here with dimethylamine versus ethylamine? Again, these two are isomers, but notice here on the secondary amine there's only one hydrogen. On the primary amine there's 2 hydrogens. Well, if you have more nitrogen-hydrogen bonds, you're going to have more a greater ability to form hydrogen bonds, and that's what increases the boiling point. You see that also when you have 3 carbons. So a 3-carbon alkane, propane, has a very low boiling point, gas at room temperature. You add a nitrogen and the size goes up a little bit, but primarily it's because this is polar now. And if you have, well, let's look at the alcohol first. So this is propanol, boiling point very close to that of water. With the primary amine, right, 2 hydrogens, 48. A secondary amine, now only 1 hydrogen, and there's an ethyl group and a methyl. So 2 alkyl groups, it's secondary. It has a lower boiling point. You get to the tertiary amine, there's no hydrogens at all attached to that nitrogen, so it has a much lower boiling point. Okay, so you see this here with these primary amines. We have electronegative nitrogen attracted to the electropositive hydrogen, and because these are primary amines, we have the ability to form, they're only showing 1 here, but we have we could have another amine hydrogen bonding to this through its nitrogen to this hydrogen, and another amine hydrogen bonding to this. So maybe, I don't know if I can do that, but we'll try it. Put our nitrogen here. And this would be the, I'm not going to try to draw the rest of the amine, but we would have hydrogen bonding to this one as well. So you could form actually 1, 2, 3 different interactions with a primary amine. With a secondary amine, if we get rid of one of these hydrogens, okay, cross that off, right? We would still be able to form hydrogen bonds through the nitrogen and through this hydrogen. But once you get to a tertiary amine, there's no hydrogens left, and so there's no ability to form hydrogen bonds. This ability to form hydrogen bonds also affects their solubility in water. So again, they're showing a methylamine here, right? This is the same compound here, methylamine, primary amine, 2 hydrogens. They're showing a hydrogen bonding with water. So here's the red atom is the oxygen, partial positive on this hydrogen, right? Partial positive on this hydrogen being attracted to the oxygens, right? Hydrogen attracted to the oxygen. And then the hydrogen of water, right? Here's a hydrogen of water, is being attracted to the, which is partially positive, being attracted to the partially negative nitrogen on the amine. So again, with a primary amine, you would be able to form 1, 2, and they don't show it, but 3 interactions with water. With a secondary amine, you'd only be able to form 2. And with a tertiary amine, you would still be able to form hydrogen bonds with water. Again, they just can't hydrogen bond with themselves. So well, first off, remember this. If they're 5 carbons or less, they're going to be soluble, but that solubility drops off as the alkyl chain gets, or as the number of carbons gets bigger and bigger, because the only polarity in these molecules is from the nitrogen and these hydrogens. And if you add more and more hydrogens, if you add more and more carbons, the carbon is not polar and it will not be soluble in water. So less than 5 carbons soluble. After that, they still dissolve a little bit, but the solubility drops off. So let me show you what happens if we, let me show you if we have a tertiary amine, right? So 1, 2, 3 carbon-carbon bonds bonded to this nitrogen. Now the nitrogen has an unshared pair of electrons and it's partially negative. I'm not going to attempt to draw the delta negative, but it's partially negative. And then of course water, we'll make water blue. Water, we can form now hydrogen bonds between the partially negative nitrogen and the partially positive hydrogen of water. So even though there's no hydrogens in a tertiary amine, it can still hydrogen bond with water, and so it will still be soluble, although not as soluble as secondary and not as soluble as primary. So we can summarize that here. 5 carbons or less. And as far as solubility goes, a tertiary will be less soluble than a secondary. Secondary less soluble than a primary. All right, so a little practice here. Which of these compounds has the highest boiling point? Well, the first thing you want to look at is to see, are they all about the same size? And they are. They all have 3 carbons. Right, so they each have 1, 2, 3 carbons and a nitrogen. So propylamine, you have methylethylamine. And then here we have just butane, 1, 2, 3, 4 carbons, no nitrogen. So, but they're still all about the same size, so we don't have to worry about that. If they have the same functional group, so say for example, this has 3 carbons and 1 nitrogen. If this had 1, 2, maybe 3rd carbon out here plus a 4th here, this you would expect to be have a higher boiling point because it's just simply larger. But since they're all about the same size, what we're looking at is, okay, well this one's primary. All right, so this one's primary. This one is secondary. So a primary will have the higher boiling point. So 1 will be greater than 2. And what about number 3? Well, number 3 is simply an alkane. So there's no polarity at all. So that'll have an even, I'll put 2 less than or greater than signs. 1 is greater than 2, which is much greater than number 3. And I'm using the numbers here. I don't mean to indicate that this is a tertiary amine. Which compounds are soluble in water? Well, both 1 and 2 will be. They're less than 5 carbons. 3 is not. 3 is not soluble because there's no polarity here. This is just an alkane. Okay, so as I was saying, number 1 has the highest boiling point. Number 2 a little bit lower. Number 3 the lowest, and both 1 and 2 are soluble. So we talked about the naming, classification, structure a little bit, the physical properties. Now let's talk about the chemical properties. One of the most important things to remember about amines is that amines are organic bases. So remember, there's an unshared pair of electrons on the nitrogen. It has a complete octet, and the hydrogen, one of the hydrogens from water, is attracted to that unshared pair of electrons. So it gains a pair of electrons. It's an electron pair acceptor. That's the definition of a Bronsted base. Bronsted bases are electron pair acceptors. So again, remember way back to, what was that, chapter, I want to say chapter 8 maybe. So NH3 gains a proton acceptor, becomes NH4. Water loses a hydrogen. Instead of being H2O, simply OH. So another definition for Bases are things that dissolve in water to produce hydroxide ions. Now, the hydroxide ion here isn't coming from the base, it's actually coming from water. So let me hear, this is the organic base. So B for base. Water is the acid in this case. It's the organic acid, or not the organic acid, it's it's acting as the acid. Ammonium ion is in the reverse reaction. Now these are weak bases, so we have an equilibrium in the reverse direction. Ammonia is donating a hydrogen ion to the hydroxide ion. Right? So it's the acid is donating the proton, and the hydroxide ion, of course, the quintessential base, is accepting that proton. Proton acceptor is a base to form water. In amines, all we've done really is replaced one or more of these hydrogens. The business end of amines or ammonia is the nitrogen with this unshared pair, and that's going to be present whether it's a primary, secondary, or tertiary. So all amines will undergo this sort of reaction with water to produce the ion plus hydroxide. Now notice we go from ammonia to ammonium. With amines, this would be methylamine, methylammonium. So it's the exact same term here, right? Ammonium. But it's got a methyl attached to it, so methylammonium. One other thing to be careful here, ammonium has 4 hydrogens. Well, remember, in an amine, we replaced one or more of those hydrogens with an alkyl group. So with a primary amine like this, it's going to have 3 hydrogens because we replaced one of them. So just because it says ammonium, don't think it's NH4. Here it's NH3. Another reaction of amines, and again, remember amines, if these are bases, right, an amine is a base. I can write base easily. All right, so what do bases do? Well, acids and bases neutralize one another. So an amine will dissolve in water, produce hydroxide ions. It will react with an acid. HCl is an acid, right? Hydrochloric acid. It will react with an acid to form a salt. But instead of the typical reaction where we had, I'll do it this way, if we had sodium hydroxide and a OH plus HCl in those reactions, so that's really sloppy, I'm sorry, but sodium hydroxide plus HCl gives you what? It gives you the salt, sodium chloride and water, right? So NaCl plus H2O. So the OH and the H here is what comes together to form water, right? OH and H here, right? Well, in this reaction up here, we don't have an OH. So we don't form water, but we still form the salt. So the hydrogen ion is donated to the amine, just as before, with the reaction with water, but of course it's not with water, it's with this acid. So this donates a hydrogen, right, to that nitrogen. NH2 becomes NH3. And it's an ion now, right? It's gained a proton with the positive charge, so it's methylammonium, a plus charge, and what's left is a chloride ion, so that's the counter ion. So you form the salt methylammonium chloride. Now, one of the important properties of amine salts is because it is a salt, is an ionic compound, they're much more soluble. So many drugs are formulated as salts for a number of reasons. One, they're going to be solids at room temperature because they're ionic, and they're much more soluble, so they're absorbed better. So if you look on some medicines, you might see something like ephedrine HCl or ephedrine hydrochloride. What that is a chloride salt of ephedrine. Okay, Benadryl, again, it's the chloride salt of diphenhydramine. So it's not just diphenhydramine, is diphenhydramine HCl. They react it with HCl, or diphenhydramonium chloride if you wish. So one of the key things here to recognize is that amine salts are more soluble and that they're solids at room temperature. Another drug, although maybe not a medicine so much, cocaine, HCl, is known as crack. Right? So crack cocaine. Here's the business end of the molecule. It's the ammonium. The chloride really would be attached to, or would be bonded to this nitrogen. I don't know why they put it way over here, but it should be over here. If we react this with sodium hydroxide, they don't show it, but the sodium combines with the chlorine to make sodium chloride, and the hydroxide ion here reacts with this hydrogen to form water. So again, you'll form a salt, NaCl, and water, HOH, and then what's left is this. This is known as the free base. It's a tertiary amine. There's two. There are two carbon-carbon bonds here, a third one here. So there's one carbon bond, two. So three carbon-carbon bonds is a tertiary amine, but it still has this unchaired pair of electrons on the nitrogen, and that's what bonds to the hydrogen. Okay, so you get 4 bonds then around this nitrogen. 1, 2, 3. The fourth bond would be through this unchaired pair. I can put them here to that hydrogen. So when there is, when it's just the amine, it's not the salt, it's not the ammonium, like the methyl ammonium or something like that. It's not the salt. It's referred to as a free base. Let's say write the equation for ethylamine when it reacts with each of the following. So ethylamine, right, that's 2 carbons. I'm not going to do the whole reaction because it's too difficult with this goofy pen, but we have 2 carbons attached to a nitrogen, and this is a primary amine. Ethyl, there's only one alkyl group, this ethyl group, so that means we have 2 hydrogens. All right, so there's ethylamine. When it reacts with water, the water acts as an acid and donates a hydrogen to this unchaired pair of electrons in the nitrogen. Becomes NH3+. We get the ethyl ammonium hydroxide. Okay, so ethyl ammonium here, and then if water loses 1 hydrogen, it'll be the hydroxide. When you react with an acid, you get the ethyl ammonium chloride, the salt. So again, you see the ethylamine react with water, get the ethyl ammonium hydroxide. When it reacts with an acid, you get the ethyl ammonium, still ammonium, right? NH3+, but chloride, the salt. So this is a salt, this is the ammonium hydroxide.